Alright, in this video we will be answering some questions about rational functions. And rational functions are functions where you have a numerator and denominator, and you have some sort of a polynomial in the numerator and another polynomial in the denominator. Now, for problem number 5, we're supposed to write our own rational function given the vertical and horizontal asymptotes. Alright, now our function doesn't have to be perfect and hit every single point. I'm just going to make a function that has the correct vertical and horizontal asymptote. That's all I'm really going to worry about right now. Even if the branches are in the wrong place, that's going to be okay for me right now. So let's start with the vertical asymptote. You see that I have a vertical asymptote at -3. Okay, so I've got a vertical asymptote that is x equals -3. Now, vertical asymptotes come from the denominator of a function. So right away that tells me something. Okay, if I'm going to have a vertical asymptote at -3, that would happen if the denominator were x plus 3, because you set it equal to 0 and solve to get the vertical asymptote. So far so good. Now, I have a horizontal asymptote at y equals 2. Alright, I have a horizontal asymptote at y equals 2. Now, horizontal asymptotes are more complicated because I have to deal with the degree. Sometimes the degree of the numerator is less than the degree of the denominator, but in that case, the horizontal asymptote would be y equals 0. Alright, I don't want y equals 0, I want y equals 2. So I need to make sure that that is not the situation. I need to make sure that the degree of the numerator is not less. If the degree of the numerator is greater, then there is no horizontal asymptote. So I don't want that either. So my only hope at getting y equals 2 is for the degree of the numerator and denominator to be equal. If they're equal, then you get the horizontal asymptote by dividing the leading coefficients. So I need the degree to be equal. But look, I already have the degree of the denominator is degree 1. See the x? So I need to make the numerator also be degree 1, so they'll be equal. So there, I can just put an x. So now they have the same degree. So right now, the horizontal asymptote is y equals 1, because the leading coefficients are 1 and 1, which gives you 1. But I don't want it to be 1. I want it to be 2. So as long as I'm using these leading coefficients, all I have to do is change this. So instead of being a 1, I need to be a 2. So now the leading coefficients are 2 over 1, which will give me y equals 2. So that's it. That would solve the problem. Alright, so that's it. That's the answer to the question. Technically, there's one other way I could have done it, so I'm going to show that as well. Alright, but this is kind of what I think of first. The other way is this. If I made the top degree less, okay, so say if I just had 1 over x plus 3, for example. Alright, or any number. It doesn't matter what this number is. It could have been a 5 or a 7 or a 13. But if the top degree is less, then right now that means the horizontal asymptote is y equals 0. I still have my vertical asymptote at -3. Now, if I want the horizontal asymptote to shift to 2 instead of 0, instead of changing the numerator like that, I could simply add 2 on the end of the function. Alright, that would shift the entire function up 2, and it would move the horizontal asymptote from 0 to 2. So this would also have the same properties. Alright, so both of these functions would have a vertical asymptote at -3 because of this, and both of these would have a horizontal asymptote at 2. So either one of these answers could be correct. So that was number 5. Okay, let's basically do the same thing for number 6, but this time we're given the numbers instead of a picture. So here I go. So f of x equals vertical asymptote at 5. That means x minus 5 in the denominator. If my horizontal asymptote is at -3, so again, there are two ways I can get a horizontal asymptote at -3. One way is to make the degrees be the same. If the degrees are the same, then we're going to divide leading coefficients. So if I make this leading coefficient -3, then that's -3 over 1, or y equals -3. So that's one answer. Or, okay, again with the x minus 5, if I put any constant up here, like a 1, right now the horizontal asymptote would be y equals 0, the way it is now, because the top degree is less. That's automatically y equals 0. If I want to shift from 0 down to -3, I could do that by putting a -3 on the end. So both of these would satisfy these criteria. All right, for number 7, we have some nice function analysis. Vertical asymptote, we have two of those. We have a vertical asymptote at -3. You just have to remember to write x equals -3. And we have another one at +3, so we will have x equals +3. We have a horizontal asymptote down here at -4. Horizontal asymptotes are y equals, so y equals -4. I see we have a hole here at 8, -4.5. So I'm just going to write that down. 8, -4.5. There's a hole. Now the domain. The domain is broken up by vertical asymptotes, all right, because you can't touch those. But it's also broken up by the hole at 8. There's no asymptote here, it's just a hole, but nevertheless, when I do the domain, I'm going to have to pause at 8 and skip it with the union. So look, watch this. I'm going to wind up doing my domain from -infinity to -3, skip it, -3 to +3, skip it, +3 to 8, skip it, 8 to infinity. All right, so see how the whole also has to break up your domain. So I'm just going to basically write down what I just said. So -infinity to -3. It's a horrible -infinity. All right, -infinity to -3, union -3 to +3, union 3 to 8, union 8 to infinity. Okay, so there's your domain. It has to be in 4 pieces. All right, for the range. Now you know that range goes from bottom to top. Okay, you just have to watch out for your horizontal asymptotes. Okay, so look, as you look at this graph, let me make a bar real quick, if I may. Students have trouble with the range sometimes. So let me use this bar to help you see what is happening. Okay, so this bar detects the presence of a function. Imagine that it does. Okay, so anytime this bar touches the function, it's going to make a sound. So watch this. Beep! All right, it's beeping because it's touching the function. So as I come here from -infinity, this graph is going to make a sound as it touches the function. As I go from negative infinity to positive infinity, this is the sound it will make. Beep. Beep. All right. Now, did you hear there was a pause where there was no beep? It was beeping from negative infinity to here, but then from the horizontal asymptote to here, there was no sound. Because there's no part of the function that's present between the horizontal asymptote, between the horizontal asymptote and this local min. So this whole empty desert area needs to get left out of the range. So that's why the range is going to go from negative infinity to -4, okay, and then nothing, and then union 0.6 to infinity. That's how it's going to work. Okay, so negative infinity to -4, union. Now watch this. I'm going to have a bracket at the 0.6. All right, 0.6 to infinity. Because at the 0.6, there's no asymptote here. The graph touches 0.6. Right there's a dot right there. It touches it. So I'm going to include the 0.6. All right, I'm not including the -4 because this is an asymptote. It never does get reached. All right, how about y-intercept? Well, the graph touches the y-axis right here at 0, 0.6. How about x-intercept? There is no x-intercept. The graph doesn't touch the x-axis anywhere. Okay, now let's talk about increasing and decreasing intervals. From left to right, going across the page. Sometimes we're going downhill and sometimes we're going uphill. Anything that's going downhill from left to right is decreasing. Uphill is increasing, of course. So from left to right, this part of the graph is decreasing. And picking up over here, I'm decreasing. And then I start increasing. Okay, and then I have to skip, and then I'm increasing again. I'm going uphill. I still have to skip this hole though, so watch out for that. All right, don't include this hole in your increasing interval. Okay, you're gonna have to skip it just the same way we skipped the asymptote. Okay, so my increasing intervals are the green parts, and there are 3 of them. One here and one here. Now, even though we ran out of graph space here, you can know that this will go all the way over to the asymptote. Okay, so these are all x values, okay? So on the x-axis, this green goes from 0 to the asymptote at 3. So 0 to 3. That's increasing. Then union. Now see this piece right here? Just this piece, okay, right up to the hole. So on the x-axis, this piece goes from the asymptote to the hole. So that's 3 to 8. Okay, and then there's one more piece that on the x-axis goes from 8 to infinity. Looks so pretty. You guys look so pretty.
Thank you.
So I'm going to go from 8 to infinity. Okay, so those are my increasing intervals. Now decreasing are these pink parts here. So on the x-axis, this part right here goes from negative infinity to the asymptote. You can know that we'll go all the way to the asymptote. So negative infinity to negative 3. Union. And then I have one more pink part that on the x-axis it goes from negative 3 to 0. Alright, for increasing and decreasing intervals, they will always be round parentheses, never square brackets. Okay, like for instance, even right here at 0, it's decreasing on the way there and it's increasing on the way out. But right at 0, it's neither increasing nor decreasing. It is flat. Okay, now for the end behavior, it's a matter of what's going on the left and what's going on the right. So as the graph goes to the left, it's approaching, I'm talking about this part of the graph right here. So on the left, the graph is approaching the horizontal asymptote of negative 4. Right? It's not going up, it's not going down, it's flattening out at negative 4. Okay, so the end behavior, I wish I had a little bit more space. Actually, you know what? I think I'll put the end behavior right here. So here's how we say the end behavior. We say, as x approaches negative infinity, that means as we go to the left, the function approaches, and in this case it approaches negative 4. Now, on the right hand side, we're talking about this. Okay, so we say as x approaches positive infinity, all right, that means as we go to the right, f of x approaches, and once again, the graph is approaching the horizontal asymptote at negative 4. And look guys, whenever there's a horizontal asymptote, it's always going to show up at the end of your end behavior every single time. All right, notice that it doesn't matter about the middle part, all right? It doesn't matter, don't say anything about negative 3 or positive 3, and for goodness sake, don't say anything about, oh, positive infinity, okay? End behavior is just left and right. The middle has nothing to do with it. Okay? And okay, what type of discontinuity is at negative 3? So look, just vocabulary-wise, we learned that an asymptote is called an infinite non-removable discontinuity. Infinite non-removable. So that's what's happening at negative 3. You have an infinite non-removable discontinuity. Whoops. Okay, and we learned that a hole is a removable discontinuity, first of all, and it's called a point discontinuity. So a hole is a point removable discontinuity. All right, so that was just a recall of vocabulary. All right, I know this video is getting a little bit long, but this multiple choice, I think we can wrap this up pretty quickly. Which of the following has a horizontal asymptote at y equals 0? Well, remember, we have learned that the horizontal asymptote will be y equals 0 when the degree of the numerator is less than the denominator. So that's all we're looking for? We're looking for the one where the degree of the numerator is less. All right, the degree of the numerator here is 0, and that's 1. 0 and 1. 0 and 1. So all of the above. All of these have a horizontal asymptote of y equals 0. What about number 9? Which function has a vertical asymptote of -3 and 1/2? So the idea would be to factor these and see which one's going to give you -3 and 1/2. I don't know which one it's going to be, but let's just start factoring. So let me grab this one real quick. So if I were to factor this, this would give me 2x times x, 3, okay, if I'm shooting for it to be 1/2 and, -3, then, in fact, that would be a smarter way to do this. Rather than factoring all these, let's make the factors ourselves. So if I'm going to have x equals -3, that would come from a factor of x plus 3. Don't you see? And if I'm going to have a 0 of 1/2, that would come from a factor of 2x minus 1. All right, now that might be tricky for you to picture, many of you. So you might have to do more of the factoring thing, but I'm sure you saw the x minus 3. But can you see that if I had 2x minus 1, if I set that equal to 0, I would add 1 to both sides, so that would give me 2x equals 1, and then I would divide by 2, and that would give me x equals 1/2, which is what we want. So my factors should be x minus 3 and 2x minus 1. All right, now if I multiply these together, by doing the double distributive property, that should help me see which one it's going to be. And you know what? Look, both of these are the same. Both of these denominators are the same. So if this turns out to match this, then it must be all of the above. But let's check it out. I'm betting it's all of the above. If we double distribute right here, that's going to give us 2x squared. And then x times -1 is -x. And then 3 times 2x is 6x. And then 3 times -1 is -3. So combining like terms, we have 2x squared plus 5x minus 3. So that means both of these are going to factor, and we could have just factored it, okay? I could have just sat here and finished factoring it, and I would have gotten 2x minus 1 and x plus 3 for both of these. Okay, so both of these are the answer. So if I have 2 of them that have these vertical asymptotes, so that means one of them can't be the answer. So it must be all of the above. And if you look at this one and you say, wait a minute, that's not the same. Well, GCF. If I pull out the 2, that's a common factor here, what's left behind? This quickly becomes 2x squared plus 5x minus 3, just like all the others. So, once again, all of the above is the answer. Okay, what about number 10? What are the x-intercepts of this graph? Well, the x-intercepts are going to come from setting this equal to 0 and solving. So the way I do that is by factoring. Okay, so x squared can only be x times x. 21 is probably going to be 3 times 7. Inner plus outer equals middle. So inner, I have 3x. Outer, I have 7x. I'm trying to get positive 4, so I'll need a positive 7 and a negative 3. So there's my negative 3, there's my positive 7. Also, negative 3 times 7 does make negative 21, so it checks out. So this is how you factor it. But to go ahead and get the x-intercepts, I need to go ahead and solve this equation by setting each of the factors equal to 0. So that's going to give me x equals positive 3, because I have to add 3 to both sides, and x equals negative 7, because I have to subtract 7 from both sides. So these are my x-intercepts. We'll be at positive 3 and negative 7. So I see those are right here. Okay, so the answer is B. Now I'm not sure why they're so far away. I'm not sure why they're so far away, but this is B. All right, which of the following has a slant asymptote when graphed? Well, slant asymptote happens when the degree of the numerator is 1 greater than the denominator. That's when you're going to have a slant asymptote, as long as you have a remainder. So let's look for the ones where the degree of the numerator is 1 more than the denominator. So let's see. Nope, not this one. All right, the numerator is less. These are the same, or same degree, degree 1, degree 2. Okay, we're looking at the exponents. All right, 1 and 1. This one, C, degree 2 and degree 1. So the degree of the numerator is 1 more than the denominator. So that's why C is going to be the answer. This one, the top degree is more, but it's 2 more. It's got to be just 1 more to have a slant asymptote. So it's not going to be this one either. So that's going to be C. Now, which of the following has a hole at x equals 5? Now, a hole happens when you have a factor that cancels out in the numerator and the denominator. Now, all of these have a factor that cancel out, so we just need the one that's going to give us x equals 5. So if you look at A, for example, this is x plus 5. The numerator factors as x plus 5, x minus 5, okay, over x plus 5. So the thing that cancels out is x plus 5. So that's where the hole is going to be. But to get the hole, you have to set this equal to 0. If I set x plus 5 equal to 0, that's going to give me x equals negative 5, not positive 5. So the answer is not A. Okay, what about B? Okay, for B, again, I'm going to have x plus 5 times x minus 5. All right, this is the difference of 2 squares. In the denominator, I'm going to have my x minus 5 still. Now these are going to cancel out, and that is going to give me a hole. Okay, so I will have a hole, and to get the hole, I'm going to set x minus 5 equal to 0, and I'll have x equals 5. So there will be a hole at x equals 5, which is what I wanted. Okay, so B is looking good. But let's look at C. At C, in the numerator, of course, I have x minus 5. In the denominator, again, I have x plus 5, x minus 5. Again, x minus 5 cancels out. So again, I have x minus 5 equals 0, shows me where the hole is. Adding 5 to both sides, I have that x equals 5, which is what I wanted. So I will have a hole for B and C, which is one of my options. So the answer is D.